All right. Welcome, everyone, to the Torch-MLIR community meeting for the month of June. This is the agenda for today. We have quite a bit of stuff to get through. So first, I'll cover some stats updates on what's been going on in Torch-MLIR. Anush will cover some of the workload updates that him and his team has been able to get going in at Node. And then we'll have a presentation from Maximilian on testing against Stable PyTorch, another presentation from Matthias about transformers, makeFX, and reproducers. And then Max will give a presentation about the pure Python importer that was recently landed in Torch-MLIR. All right, so before we get to that, a few reminders. So this is the monthly community meeting that happens the first Monday of every month at 9 a.m., where we cover major updates about Torch-MLIR, and it's recorded every single time. And then every other Monday, we have the developer hour, also at the same time. And it's more for technical discussions. It's not recorded. And you can just come and ask any questions you have about Torch-MLIR in there. And every Thursday, there's also office hours with me from 8:30 to 9:30 a.m. And that's more for entry-level questions about debugging, implementations, and so on. And so I'm happy to help with any of that. There's also a Discord, which is very active. So if you're not there, do join. And of course, we have a discourse on LVM. So this we didn't have a community meeting last month, so this is 2 months worth of data, but fairly active couple of months, 121 commits in 63 days. And these are all the contributors. Thank you, everyone, for all the hard work on that. In terms of ops, there's been, all 3 backends considered, 25 new ops, 17 improved ops, which is quite nice. So thank you all for that. And now I'll hand it over to Anush to give us updates on workloads.
Cool. Thanks, Ramiro. I think the main one that we've been focused on is Llama and Llama variants like Vicuña and all that. That's the new hotness in LLMs with GPT-Q quantization. I think as of last week, we've been able to lower 2 Linalg with obviously Torch dialect and Linalg with GPT-Q. And we're just validating that on both CPU and CPU, Vulkan, and then CUDA also. The second one we are working on is called Mini GPT-4, which is something that builds on top of Vicuña. So it's Vicuña plus QFormers plus VIT. It's not fully done yet. I think it's just there's some Vicuña issues we have to fix for some shapes that are required for Mini GPT-4. But Mini GPT-4 is basically a multimodal model, and we hope to have that soon too. That's also like a customer requirement, and these are all models that we are planning to deploy in customer setups. And then there's another one that we've just started working on called local GPT or private GPT. But basically, it's line chain plus instruct embeddings plus Vicuña. The best way to think of it is like it's Chat GPT for your local PDFs and data and everything. It basically creates a vector data store locally. It's like Google Desktop V2 basically, but with Chat GPT like interface for Google, the old Google Desktop. That's also another thing that we're working on. But basically, all these models as they come up, mostly there's some tweaks here or there, but I think overall we're just kind of pushing the envelope in terms of being state of art for lowerings. So all of these things lower pretty well. And then I just added a note on, it probably should be in the CI section, but it's we got the AR64 nightly build set up, and So this basically allows Torch-MLIR to work out the box for Jetson, Raspberry Pi, Qualcomm RB5, all of those robotic platforms, etc. And also for like Graviton and these things. Just makes it easier to deploy. And so we added this. We also added, so basically Shark now works on ARM64 builds, and the Torch-MLIR part is also pushed up as a nice nightly build. Those are the main things. Any questions? Happy to answer. Okay, we'll hand off to Ramiro.
Cool, awesome. Yeah, thank you for that. Let's now go on to our first presentation. Let me see. I think I can give you co-presenter access so that you can control the presentation.
Okay. First of all, can you hear me?
Yeah, I can hear you.
Perfect. Yeah, I can change slides. Thank you. Yeah, so I'm Max. I'm from the AMD Cologne team, and I will give you a very short presentation on our work on testing against the Stable PyTorch version. So you probably all know that, but we at AMD, we wanted a stable version of Torch, and those are all the reasons why we wanted it. So it's just less ambiguity for different frameworks. So when we have a PyTorch release, we know exactly which Onyx Object version is supported. And we also know when we have a stable release, which features are in which state and which are still marked experimental. A very, very important topic for us was that we don't want to ship a nightly PyTorch version to our customers. It was probably the most important part here. But from a developing standpoint, it's also really nice to have a stable version, because now dependency changes are less frequent. And when you have a lot of developers working on a project with a lot of dependency changes, it's painful for everyone. It also makes it predictable which packages are compatible and which are not compatible with each other. And also, sometime in the future, we could enable a systematic version testing with different PyTorch versions. Okay, so now if you open a new PR, different than before, you will now see 6 CIs that run. So we're currently only using the Linux builds for the stable testing. And at this point, I want to give a big thank you to Node.js and Google and the whole community for the reviews and support. It was really helpful. Wouldn't have been possible without you. And now you're probably all interested in the stats and how painful the transition was. So it was easier than expected. So I had to deactivate 3 tests, 1 lit test and 2 npm tests in Linux. And they were all failures because of buggy or non-existent ops in Torch. They were big disclaimers in the Torch file, like this op has to be deleted or whatever. So those were ops that didn't work. Which was also interesting that for the LTC backend, the nightly version was performing worse than a stable version. So we have 24 unexpectedly passed in the testing right now. And all in all, I would say the integration was less painful than expected, which was nice to see. So what we landed was an MVP. It's not finished. And here just a few bullet points of what could be improved. So as you saw before, we now have 6 CIs that run every time. Before we had 4. And there was already discussions on which to enable, which not to enable. So one idea was only in-tree and nightly and out-of-tree and stable. But there was also a Discord discussion about just having all of them activated because the load on the runners was not too high. So, but we have to keep an eye on that, I think. Also, if we have more experience with the stable builds, at least in my opinion, we should at least mark 1 stable build as required to pass for PR. But it's probably too early for that. We have to get more experience with them. What we have with the nightly dependencies that are these automatic PRs that always select the newest dev build, and they create a PR with that. That's currently also missing for the stable ones. So we're now defaulting to the newest stable version of Torch and Torch Vision. But it would be nice to better track that with PRs and have separate testing when a new version comes out. So that's also currently missing. And also when I looked through the test failures, there were also some parts or some groups of tests that require a certain feature, like Torch Dynamo or whatever. And there's currently no classification for tests that could be enabled in batch or not. So I would think about something like it requires Dynamo as a Python decorator and have an infrastructure for that. Or whatever the reason, I'm happy for feedback here. And then we can group tests into different chunks and activate them or deactivate them as we need. Currently, with the deactivated tests, we are just using the package.version utility, but it's a bit clunky and also is very unpredictable with the .def ending and the plus CPU ending. So we already had bugs with that. It's not the nicest thing to use. Contribution here are more than welcome. Would be happy to get feedback from you and also how to enable you to use the stable versions here. Thank you. Do you have any questions?
Awesome, thank you. I do have one question. So is there a way for, if someone goes to Torch-MLIR, like how could they tell what's the latest stable version that works with Torch-MLIR? Do we keep track of that somehow? I know for Nightlies we have like the releases page that sort of links the Torch-MLIR with the nightly version.
Not currently. So in the draft state, I specified the version in the pip install command, but we had discussions about we don't know when this automatic rolling will come in, and always manually updating packages was also not the best thing to do. So we just defaulted to the newest version, and there's not really a way to tell right now other than the newest version works.
Gotcha. Okay.
Yeah, I think we should, when we have the infrastructure for it, we can update it. But for now, the releases page, the ARC64 build has the Torch version, stable version also, so you know the last stable version that you're using. So you'll see like a Torch binary that's 2.0.1, but hopefully it'll, you still have to install that. And but I think going to like supporting a set of stable versions can be like a future thing where we set up a CI that we just test across a bunch of stable versions. And then we have min and max PyTorch versions that we can support.
Cool. Any other questions? All right, I'll hand it over to Matthias then to give the next presentation.
Thank you for pushing along here. Is like intricate, but thanks for pushing along and getting it to land.
Yeah. There were a lot of things to consider before getting it in. So yeah.
Great. So hi, I'm Matthias. I'm also working with Max in the AMD Germany Cologne office. And I want to discuss 3 topics with you today, starting with transformers. So roughly a month ago, we assembled a team in Cologne to check the readiness of Torch-MLIR going from PyTorch to TOSA on a bunch of transformer models. So we assembled 136 model configurations of Hugging Face transformer models and tried to all run them through Torch-MLIR to TOSA. And we did this for all the models in bflow 16. And our goal was first to figure out what does currently work and how does it look like, but also figure out if we see any issues, are those issues going to be significant or are they going to be easy to fix? So we tried to fix as many issues as we could in a short time to get a sense of, is this substantial or is this like a bunch of small work, right? So what you see here is that when we started months ago, 37% of those model configurations would go into Torch-IR, but only 8% of them would then also successfully go into TOSA-IR. And during the course of this month's work, we were able to increase the rates to 95% going to Torch and 73% going to TOSA. While doing this, we reported, I think, roughly 4 issues upstream, which 3 of them were kind of immediately fixed just by Google employees. Ramiro, I saw you doing that a lot, so that was very nice. And then for the rest, we accumulated like roughly 25 fixes in our current fork, which we are starting to upstream essentially now. So as a final result, we now have 1 unique error going with all of those transformer models into Torch-MLIR, and there's 9 additional unique errors when you go further into closer.
Awesome work. This is just like, and we should, I think I brought this up previously. We should see how we can get you not necessarily to have it, all those errors in the fixes in the fork. So you and your team can directly work with upstream, so that you don't have to like stage it. And obviously you can have your fork for your own, changes, but things that will go upstream and can be upstream, anything we can do to enable your team to work directly on upstream, do let us know. We'd love to have you not have to repeat the work and then upstream, right? So that you can
exactly. And I think going forward, that's also exactly what we're going to do, right? Our pace is going to slow down now considerably because we have gained some confidence in Torch-MLIR. So now when we see more issues, we can go and fix them directly by opening PRs and upstream. But our initial thing was to very quickly fix as much as possible to really figure out like what is it that we are looking at.
Makes sense. This is great to see, 126 models all the way to TOSA, right? Because for us, TOSA, we, for the Nord team at least, we've tested. We used to do quite a bit of work. Now we've kind of slowed down on that. But it's good that you've gone down that. The one unique error in the Torch-MLIR one, is that index split thing or whatever, that one? Is that the Torch?
No, that one we also fixed.
Okay.
I will go to the next slide because that's actually the list of, oh no, right. It's the next slide after this one. So here's a list of fixes.
Right.
I'm not going to read them to you. It's more for reference, but we also opened an issue on our fork where we're now going to track all of those and which of them we already upstreamed, so we can like make sure we don't miss any of those. And in the meantime, if we are too slow upstreaming and you really desperately need one of those fixes, right, then you know where you could find them. And generally speaking, I would say like maybe 20 to 30% of the fixes really affect the Torch-IR itself, and the rest is probably more on the lowering from Torch to TOSA. Right. So in terms of remaining issues, this is the ones that we still see. So the issue going into Torch-MLIR is actually not a Torch-MLIR issue per se. What we see is that we are using a flow around MakeFX, and I will talk a little bit about this in the next slide. And for 7 models, it fails to trace them through MakeFX because those models reach into the tensors and check some of their properties, partly because they need to assert something about them, or partly because they use some operators that have a bug where this happens. And so you just can't get the models traced. And then you, of course, don't get into Torch-MLIR. I think that partly we might be able to address this by changing the models themselves. And we are currently starting to work with Hugging Face to see if that's some direction they can see. The other option is probably doing something like deploying with Dynamo and then having graph breaks as those places. Yeah, those places seem to be very small, so it kind of would be unfortunate if you really had to graph break just for that thing. And then the other things, those are the ones going into TOSA, is just a bunch of operations that don't have lowerings or that have partial lowerings, but where the special case is not handled. For example, convolutions, they're generally supported in TOSA, but this example is a 1D convolution and this was not supported yet. So this is the things that we're currently working on. Right. Then going forward, I already mentioned that in the flow we are using for those models, we first pass them through MakeFX and then give them to Torch-MLIR. And we mainly do that because then we can get access to the PyTorch decomposition, the same way that Dynamo has access to them. And then during the course of the fixing that we did, we tried as much as possible to just use an upstream PyTorch decomposition instead of implementing that op in Torch-MLIR, because that was much easier to do. And then also sometimes we did a decomposition and at least the resulting ops were still not supported, but they were much easier to implement, right? Because they broke down into some of the prims ops and they were much easier to catch and test and implement than implementing the big op itself.
I think cumulative sum was an example, Matthias, wasn't it?
Right.
There's an upstream PR for it, but by decomposing to prim sum, we could just build on existing behavior.
Exactly. There was actually two steps, right? We had A10 cumulative sum, which was not supported at all, even in Torch-IR. Then we used the PyTorch decomposition, so we got a prims.sum, which was also not supported, but A10.sum was supported, so we wrote a recomposition in Torch-MLIR that turned the prim sum into an A10 sum, and then it passed through all the backends. And so I think there's totally like 4 or 5 operations that we added decompositions for and handled in that way. But unfortunately, when we did that, we couldn't test it anymore with a nice end-to-end testing framework that Torch-MLIR has. Because you can't say Torch test with MakeFX decomposition and so on. So something that we did on our branch was adding like an argument to Torch-MLIR compile where you can say, hey, please use MakeFX. We use the same decomposition table as the Dynamo backend uses to make sure we are kind of representative. And then we added a new end-to-end configuration, which is a combination of MakeFX and then goes into TOSA. And I guess that's the biggest debatable point if you want to upstream this, because I guess some people might want to do MakeFX and then go to Stable HLO, or MakeFX and then go to TCP. But if we do all combinations, then it's going to explode. So I'm not sure how we're going to solve this. I see like on the input, we have Torch script, MakeFX or Dynamo, and then the output, we have all the backends. And I don't know if you really want to test all combinations or what's the best way to do this.
So we already have a somewhat similar problem in terms of the Torch-MLIR's own decompositions. And this is something where we'll want each, basically each backend to maintain its own list of decompositions that it prefers. And then we'll somehow make that available to users, or somehow make that be the main way that you interact with the system. So I don't think there's like a single simple solution besides just making it documented and supported which decompositions are needed for which backend. So
in terms of testing, would you then add all those configurations to the end-to-end testing CI?
Yeah, what I'm saying is like instead of like n squared possibilities, there would just be n, because it's like each backend would sort of know what are the right decompositions it needs. Does that make sense?
Like there's one for MakeFX, but then maybe you still want to test what happens if you just do Torch script to and then go to TOSA without MakeFX, or what happens if you do Dynamo and then go to TOSA. Right, you still have at least those 3 different ways.
I think if we have to test it, the CI can. We don't have to optimize for the CI testing.
Okay.
I think what we have to do is make sure that the API is right, and if that requires few more runs of like combinations, that's okay. Right.
Yeah. Also, longer term, I think we're gonna just go to Dynamo when it's just ready. But right now, it's not ready enough. So this is like a nice way to already get access to the decompositions before Dynamo is ready.
Yeah, I agree.
We have the same problem with Shark. Like Dynamo is kind of, the marketing train is much ahead of like the product train, right where it is. So so everyone's like, oh, Dynamo, but it doesn't work on 3.11, doesn't work on Windows, it doesn't, but then we have to shift to 3.11 with Windows, right? So we use MakeFX quite a bit as an escape hatch, and I think we should leave those escape hatches available.
Yeah, also, I think this is something that this whole like op decomposition matrix thing is something that I think PyTorch is slowly getting better at. So my understanding is they're trying to converge on like a core A10 subset. And then hopefully over time, somehow we'll be able to convert the core A10 subset to our backend dialects in some simpler way. I don't have like specific knowledge of what's the best way forward, but I think this is something, it's just kind of nasty now, and we're just going to have to, add more CI configurations or whatever is needed for the current situation, unfortunately.
Okay. And then the last thing I will talk about is a tool we wrote or proposed, which is a reproducer minifier thing. We were working on those huge transformer models, which contain like 1,400 ops, and then Torch-MLIR would fail on something with an error message. For example, saying unknown rank, there is a static tensor cast here. We try to figure out what this is. So we made use of a thing called functor compile minifier, which allows you to minify FX graphs by preserving some property. So we first capture the error message that Torch-MLIR generates. We sanitize it into a format that is fine if you change IR a little bit, like getting rid of SSA names and so on. And then we use this function to reduce a graph by making sure that Torch-MLIR would generate the same error message, trying to compile that graph. So at the end, we would end up with the smallest reproducer in Torch code that would get us there. Unfortunately, we hit one bug in PyTorch. I opened the issue about it, but I'm not a PyTorch contributor, so we didn't figure out any of the like contributions, legal stuff, and so on. It contains a 2-line fix that you need to apply to make this work correctly. So if anybody is already a PyTorch contributor, feel free to pick it up. And then I want to show you quickly how this looks like in practice. So what you would do is like you have a big model, something from Hugging Face, and you have some input args on how you trace it. So you would call the function that we created, Torch-MLIR reproduce on the model args output type. It kind of looks like compile, right? Just reproduce. And then it would run it. It would capture the error. It has like a set of errors that you typically get. Would sanitize the error message, and then run for like 3 minutes, reducing the graph from 1,400 ops to like 4 ops, and saying, hey, this is smallest reproducer. If I remove any op in here, then it's not going to reproduce anymore. So it's going to do things like replacing the SSA values in the message and replacing the dims, because sometimes they change if you do reproducers. And then it outputs like the smallest code that you get. It's not perfect, because it turns out you can actually remove the slice 3 in here and return new zeros, and it still reproduces. So that's probably something we could improve in the upstream PyTorch minifier thing, but it's very useful. You just run it 3 minutes and you have a small reproducer. Like that helps us so much in going through those many models. And yeah, that's it on my side. Any questions?
And it's something you'd like to contribute if the PyTorch bug was somehow fixed upstream, I presume.
Yeah, right now we have like a copy of the PyTorch file in our fork, because you also can't monkey patch that thing. So it's a little bit hacky. I'm not sure if you're wanna do that thing upstream, but if you can get the PyTorch bug fixed, then I think it's some nice code that we could contribute.
Yeah, this is awesome.
Why can't you monkey patch?
Because the problem is in a function that's defined as a local function in a huge function that has 1,000 lines of code, which is kind of the whole code. And I don't think you can access that because it's not a function at module scope. It's like function inside another function scope. And maybe my Python tool is not good enough, but it's, yeah.
I mean, I've definitely dealt with the problem of nested local functions that need to be patched, and you have to monkey patch the enclosing function. You can, if you want to be very surgical about it, you can intervene in the import machinery to rewrite the source at load time, which sounds funny, but I actually do very consistently and very robustly lately. Yeah.
It sounds good. I didn't know that it was possible, but I'm wondering if landing like this 2-line fix upstream might be an easier thing to do. I mean, it's
somebody
triaged
it. I don't know who this person is. So I'm a contributor technically, or at least I used to be. I can get somebody to take a look at this.
Like I included the fix in the issue description, and with that it works. But yeah, figuring out the
Oh, sorry, this is just the
rights
issue.
and contributions and so on.
Gotcha. Yeah. I can do this.
Cool, thank you.
Yeah.
Yep, that's it.
Awesome. Yeah. I would love to have this in Torch-MLIR. This seems very useful for writing down errors. Yeah. I was wondering how you were getting so quickly all those like small reproducers. And now I know.
You noticed that they all looked a little bit funny, yeah?
Yeah. Yeah. But they were pretty useful, yeah, to get the errors. Cool. Any other questions from people? Awesome. I'll hand it over to Max for the last presentation.
So how does this work?
You should be able
Okay,
to.
cool. There's a UI. Cool. There's a UI. Okay. Yeah. Okay. So I'm nominally supposed to present about the Dynamo FX something importer. I don't really know what to say about this. Is Sean still on the call? Can't tell. If Sean's still on the call, this was he dropped off. Okay. So this was Sean's PR that I took over that took a little while to land. I guess the idea here is that you will use Dynamo's infrastructure to import rather than Torch script. It doesn't. So I'm not 100% sure on the exactly like I know how Dynamo works, right? But I don't know what the substantive difference is between what Matthias was talking about, which is using FX importer. I mean, Dynamo works at a stack frame level, so I guess basically you had to just, that's the distinct difference, right? Where make FX graph will trace the entire graph. Dynamo will give you graph bake break snippets of FX, IR, FX, whatever. Anyway, I don't have a lot to say about this because I haven't used this. It has landed. Ramiro wanted me to talk about this, but again, I don't have much to say about this. It's there. It's broken in the next bump to LLVM because of actually a change that I made in upstream MLIR. But so in my bump LLVM PR, I have a fix for that change. But then that PR is for some reason timing out CI, like taking 6 hours. Anyway, whatever. The thing works. I haven't tested it extensively. It might be interesting to the community. It might be interesting to you, Matthias, and your team. But the thing that I really wanted to talk about, and I'm glad Sean dropped off. So I presented this a month ago and then had to drop it, work on it, or 2 months ago, and had to drop work on it to work on that Dynamo FX thing. And so I'm representing it today because I actually hit a milestone on it yesterday, or at the end of the week, last week. So just a quick reminder, what is Pi? Pi, and I don't often make broad, like bombastic claims, but I believe in this now. Pi is first-class support for PyTorch in MLIR, and I think it's more first-class than any of the other ingress paths that we have. So that includes LTC, it includes TorchScript, it includes Dynamo, right? I think this is better. And I don't say things like that unless I really feel it, and so I really feel this, and I'm going to talk about why. Okay, so there's no dependence on PyTorch. There's 100%. You don't pip install PyTorch. It's nowhere hidden. It's nowhere buried. There's no ABI problems. There's no PyPy, shipping to the PyPI package repository. Any of these problems. This is 100% Python code plus Torch-MLIR. Okay, so sorry, before I flip to the technical stuff, this was the original description, and the way that it worked, and so I rewrote it. The way that it worked was it did a whole bunch of kind of hacky things there was like a hand-rolled dispatcher, because what it's doing is it's mapping PyTorch Python code nn.modules directly to Torch-MLIR IR. So in the repo, there's an nn modules directory that is taken straight out of PyTorch. And so there's no PyTorch libtorch A10 dependency, but there's like a philosophical dependency, although that's very, very stable code by now on PyTorch, in that there's Python code. There's nn modules code. And so what happens is you start up your MLIR IR.module, you create some SSA values that correspond to inputs, tensor values, and then you run them through this, the nn modules. And all of the infrastructure in Pi means that when you do operations on the IR values, they will immediately create the corresponding Torch-MLIR operations, right? So these IR values, which don't by default do things like overload dunder add or overload dunder mul or overload dunder set item, right? There's no such thing in upstream MLIR. There's no such thing in Torch-MLIR. The bindings aren't used that way. That's what Pi is. It's a whole bunch of like, not hacks, but you know, kind of like solid Python. I don't want to call it engineering because I don't really think of myself as an engineer, but Python engineering to make overloads and operations on these IR values work correctly and emit Torch-MLIR IR. And the first time I did this, I had to handle a bunch of like weird problems. Like the main thing is that PyTorch has operator overloads for add, right? You can have like tensor plus tensor, tensor plus scalar, blah, 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 tensor plus scalar with a alpha multiplier and all this kind of stuff. And I don't know how PyTorch handles the overloads, but you can't do that kind of type checked overloading in Python, right? Like there's one add and it will always only get called. There's only one double under add. And you can't operator overload in the same way in C++, where multiple different types of argument types determine which actual dispatch gets called. It gets handled differently in PyTorch at the libtorch level. And so I had to roll a dispatcher. I had to roll like this exhaustive, hey, you know, register all of the different overloads in a giant dictionary. When you hit a dunder, check for the input types in that dictionary, see that it matches. It kind of worked. It was hacky. It wasn't really maintainable. It got good success. But anyway, all of that has now been rewritten to work like, I think, very well, right? Again, this is why I'm saying that now this is first class support, whereas before it was kind of like a whatever hacky idea project. Okay, so all the overloading is handled and with high fidelity to upstream Torch-MLIR types. How is this done? So if you build Torch-MLIR, you know, from source or whatever as an LLVM external project, you're going to generate checkers, type checkers for the verifiers that correspond to both types and constraints. So there's a set of Torch-MLIR types, right? Like torch bool, torch int, and then those are real types. They're in the type system and they have verifiers associated with them that check on the type, on the type ID of the MLIR type. And then there are type constraints like any scalar type, any tensor value, which are not types that have a type ID in MLIR, but still correspondingly generate these constraints that are hit by the verifiers when you're instantiating those operations, operations that use those types. And so if you go digging around in the source, you can find those constraints, those type checkers, that the functions that return bool is this, is that. So I found those, I took those, and I didn't even have to do much cleaning up. I had to rename some of these things. So if you build Torch-MLIR from source, those constraint verifiers generate calls to CPP. Unwrap is a cast, right? The Torch-MLIR, how do you check if a type is a thing? You do the dot is a angle brackets to the type, right? And it's a templated cast check, blah, 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 right? So those are all CPP calls, and we're doing everything through the C ABI. So I just literally regexed those things to go from do the CPP type check to do the C API type check for the same type against the C wrapped MLIR type, right? So all these on the left that's why they look funny. Well, that's why there's an exorbitant amount of parentheses, because I didn't write this. I did a regex on the auto-generated ones during the build and replaced the corresponding CPP type check with a CAPI check, and they're all there, right? Except for one that I had to, for one PR, all of the types had corresponding CAPI checkers. Cool. Once you can check for the type, for an arbitrary MLIR type, whether it meets the constraint or is in fact one of the types in our type system, you can generate values, right? So you can generate so-called typed values. IR.value or MLIR value, that's not a typed object. I mean, it is a typed object. It's an MLIR value. It's an instance of the MLIR value class, but it's not in the same sense as a tensor or float 32 or whatever. Okay, so what determines that a PyTorch float value is a PyTorch float value? Naturally, it's one that has a type, is the result of an operation. So it's like, right, all these values are results of operations. Is the result of an operation that emitted an IR value with such and such type, right? Okay, cool. Once you have float values, once you have tensor values, once you have dict values, all these things, you can, using PyBind, create fully typed APIs, calls to the IR builders. So on the right-hand side, you see a fully typed both input and output, right? So the return value is also the correct type and gets immediately cast to the right thing when it comes out on the Python side. Overloaded calls to mul. So I have int multiplication, I have float multiplication, and I have tensor scalar multiplication. And each of these would be impossible to implement in Python as a direct call to that builder without doing an exhaustive check on Python type annotations, and as well, right? So you have to do a check between the type annotations on some Python wrapper around these builder calls and the input types. And it's fine, it works. Again, the previous iteration worked and it was just a little hacky. But this is now done by PyBind, and PyBind does do an exhaustive check. There's no way around doing an exhaustive check. You might have some bitmap clever implementation, but it doesn't matter, right? Like the fact that PyBind implemented it and it works forever for all time in PyBind and is very, very robust, that gives me confidence. Okay, once you have these fully typed calls to the builders, the next thing is I want to bind the dunders to the to a tensor shadow value, to a tensor tracer value, however you want to think about it, right? So create this thing, which you can't actually create with the current upstream bindings. I have to play a little one trick to essentially expose the header that enables you to subclass PyConcrete value. Once you do that, right, it has a check. That check checks is a tensor value. That is a tensor value is the thing that I already described. It's just a value that was returned by an operation that produced a tensor type. And this is a PyBinded class that immediately I can define dunders for. So here I have multiplication between a scalar and tensor, multiplication between a tensor and a tensor, and this is just free. Like these delegates or dispatches or whatever you want to call them are handled by PyBind and the PyBind runtime. And when I run tensor multiply tensor or tensor multiply torch scalar value, the right one is picked. So I was hacking on this at the kind of like unit test, make sure all the types are filtered through, make sure all the infrastructure works and plumbing works correctly for like 3 weeks. And then on Friday, I'm like, okay, I'm in a good state. I'm going to do this presentation on Monday. Let's see where I am with respect to PyTorch parity. Sorry, skipping ahead. I turned on the tests and immediately got, what is this, like 60, 70% parity. The way that these tests are run, Matthias, I'm looking at you, is that I pip install during test Torch-MLIR, and then I snip, rewrite on import torch as import Py. Import Torch-MLIR E2E test as import Py E2E test, and all the kind of like the config, the torch config, the annotation args. So all the test suite is the upstream test suite. So all the model stuff, that nothing has changed. That's like I don't even have it in my repo. but it is run through, so it is run in 2 ways to test for parity. It is run against Torch-MLIR to generate linalg. And then I take that linalg and I run it through PyTorch, and I lower the linalg, and then I diff. I line for line diff to compare that I'm generating the same linalg using this, whatever you want to call it, tracing system against NN module that Torch-MLIR generates by using TorchScript or Dynamo or whatever it is. I think I'm using the TorchScript test config. And there you go, like 60% coverage, right? And some minimal models that work. Going back real quick, what is it like? What did I do to the NN modules to make them work with Pi, even because they're supposed to work with Torch, right? It's the same exact thing that I just described, except I actually did the regex, the sed. Everywhere it said Torch, I just replaced it with Pi. Everywhere that it says things like torch._c.nn that calls some hidden buried op inside of libtorch, that all points to the same module that I have in Pi, which is just one ops module, which has just all the ops. And so, it's not on display here, but like torch.f._v. It goes to some random place in PyTorch. They all go to the ops module in Pi. And this works, right? And this is a stable, one thing to say is like, why do this? Well, because I don't think that PyTorch upstream is stable in any sense. We are constantly dealing with issues. We are constantly submitting bug reports that they mark don't fix. Torch Dynamo is a moving target. Castle built out of sand. I don't know. I'm not trying to take anything away from the engineering effort. They're all very good engineers. There's also like 200 of them, and they all have their own problems, and they're all developing PyTorch for themselves. And I don't think that they're very interested in PyTorch being a front end. I think they're very happy to have people contribute to PyTorch in order to improve the experience for their teams, ads, and whatever. But I don't think that they want to be disintermediated, right? I don't think that they want to be relegated to just being a front end for Erie, for some XLA something, right? So, TorchScript is on life support. FX is cool, but FX is going through this transitionary period of like, is it going to be FX? Is it going to be all Dynamo? Dynamo doesn't care about whole graphs because that's their perspective on compilation in general, that they're happy to compile a stack frame at a time. Whether you'll eventually ever be able to get a whole graph from PyTorch is unknown. I feel like the answer is no, but I'm not 100% sure. But this is a stable API, right? NN.module, which is probably like the oldest code in PyTorch, probably will never change, never changes, right? So that's why I do this. And that's it. So the one, I don't know what else to say. There are wheels I turned on yesterday for x86 Linux and ARM M1. I'm going to continue to hack on it for about another week. And then I'm going to another internship. I will continue to work on it because I believe in the project. Yeah, and I'm happy to take questions if I didn't blow all the time.
Yeah, we have like 5 more minutes for questions.
Yeah, and if there are no questions, I'm happy to piss off.
Not sure if I completely understood all the things that are going on, but
Sure.
I have a high-level question. Like,
yeah,
when PyTorch evolves over time and adds new operators or new things, what is the kind of effort that would be required with this approach to like keep up?
None, because I don't care about their offset. I only care about this code. Why do I care about their offset? The only reason anybody cares about their offset is because the only way to get a representation of a PyTorch model is in terms of that offset, right? There's only the IR or serialization or however you want to think about it that you get from TorchScript, LTC, FX, right? But that's not what you really care about. The offset speaks to their compiler.
Right, but that's not necessarily what I mean. Like also in terms of public API, PyTorch is not going to stay as it is, right? They're going to add more NN modules, more functional things to do things. Like you
So,
get a new multi-head attention module or something. What is the kind of
So-
effort that would be needed to keep up?
it's literally just s/torch/pi. What the effort that is needed is that your offset, our offset, the Torch-MLIR offset, legalizes, right? So this lowers. So the things are highlighted here, kind of happy accident. The yellow highlighted here is my IDE doesn't realize that that module has sign, that it has abs, that it has adaptive max pool 1D. It does, that module does, but that's a C extension module, that's a PyBind module, so my IDE can't introspect. So you need those, right? You just need to fill out those. And sometimes these are, so that's your offset essentially. But that offset is high level, and I don't know, it depends on your opinion. I think it's actually smaller. It is actually smaller. The public API of PyTorch has fewer of these named operations than the 2,000 some ops in native functions YAML, because they have a bunch of ops there that speak to their backends. They go through a bunch of transformation passes and have JIT ops that speak to that are never exposed. I mean, sometimes they're exposed. Sometimes you see them in torch._c.blah blah. That's leakage, right? That's like abstraction leakage. This API is fairly stable. And then when they add multi-head attention, you got to support that. You got to support pi dot or torch dot multi-head attention, whatever. But the way that you support it is up to you now, right? Entirely. Rather than like, oh, this actually transforms into some middle narrow waist, like all the convolutions splay out or they narrow in, or this thing is transformed using type promotion to something else, some overload, blah, blah. This is a much simpler API in my opinion, but that's debatable. But that's the answer to your question. You just got to fill out these yellows.
Okay, thanks.
Awesome. Yeah, thank you so much for the presentation, Max. We're just out of time, so I will stop the recording now. But yeah, thank you everyone for coming.
See you guys.
See you.
Thank you. Bye-bye.
Thanks. Bye-bye.